our group is going to be presenting on geometric algorithms, specifically the convex hull problem in 2 and 3 dimensions. So the overall structure of the presentation is going to be like this. We're going to start with an introduction to the idea of computational geometry. Then we're going to look at some geometric ideas that are pertinent to understanding the convex hull problem. And then we're going to look at the problem itself and we're going to define the convex hull problem. And then we're going to look at some of the algorithms and their complexities, along with the lower bound for the convex hull problem. And then lastly, we'll go over the 3D version of the problem and some more ideas related to it. So, computational geometry is a subfield of algorithm theory where we design and analyze algorithms that have geometric input and output. But since we know that geometry itself deals with the Euclidean space, which consists of real numbers which are continuous in nature, we only look at discrete aspects of geometric problem solving. So our problems deal with straight or flat objects and simple curves. Computational geometry also aims to provide the tools from which different application areas can build algorithms. For example, computer graphics uses a lot of ideas from computational geometry in order to build their applications. It also aims to provide a theoretical framework where we can analyze the performance of these algorithms. So let's go over a bit of history about computational geometry. So geometry in and of itself has been an incredibly central area in mathematics at the time of the ancient Greeks and the ancient Egyptians, specifically because it had a lot of direct application to the lives of those people. Furthermore, books like Euclid's Elements were also a profound influence in the study of geometry and had a long-lasting influence for like 2,000 years. Then in the 16th to 17th century, the idea of coordinates permitted an increase in the computational power that geometry had. The term computational geometry itself was coined by Marvin Minsky in his book Perceptrons, published in 1969, which was about pattern recognition. And because of the fact that computational geometry is so heavily applied in so many other fields like computer graphics, etc., that has been the incubation bed for this discipline, and that has allowed this discipline to grow. Some of the problems, some of these geometric problems that sort of made computational geometry more important are things like the Euclidean traveling salesman, the minimum spanning tree, linear programming, etc. So some famous problems in computational geometry are the convex hull problems, which is the subject of this presentation. There's also line intersections, Voronoi diagrams, and Delaunay triangulations. Then there's polygon triangulations and partitioning, optimization and linear programming, and geometric search problems as well. So let's also go over some of the geometric ideas behind the convex hull problem. So in computational geometry, we mostly consider sets of points in Euclidean space. So these set of points have to be finite, or they at least have to be finitely specifiable. That means that you can define them with a limited set of points. For example, a plane can be described with, for example, 3 points. Similarly, one can define a line with 2 extreme points. So that in that way, those geometric objects are finitely specifiable. So just to introduce a bit of notation, by RD, we denote the d-dimensional Euclidean space. A D tuple would be a point in RD where each element of that tuple would be a real number. A polygon in R square is defined by a finite set of line segments where each extreme point is only shared by exactly 2 segments called edges. And similarly, a polyhedron in R cube, which is basically an extension of a polygon in an additional dimension, is the finite set of plane polygons such that every edge of the polygon is shared by only one other polygon. So now we look at the convex hull problem itself. So before we look at the problem, let's go over a few definitions. So a convex set is a subset of the Euclidean space where if I take any 2 points within the set would also contain the whole line segment joining those 2 points. A convex hull of a shape would be the smallest convex set containing that shape. And The convex hull can also be thought of as the intersection of all the convex sets of a given subset of Euclidean space. It's also important to note that that the number of convex sets for any given number of points is uncountably infinite. So before we move on to the problem, let's go over a motivating example. So imagine you have three substances which are made up of two chemicals, a combination of two chemicals in fact, A and B. And you are given the concentrations of those two chemicals within each substance. So the question is, can you use these three substances to form two other substances called Q1 and Q2 with their own concentrations of A and B? So sure, there are ways to do this formally and mathematically, but let's go over a very simple idea which would involve convex hulls. Let's first plot these values. We can see that we've plotted S1, S2, and S3 relative to their concentrations of A and B. And we've also plotted Q1 and Q2, which are the two chemicals that we want to create. So we see that with the line joining S1 and S2, if we choose any combination of concentrations along this line, we will obtain some chemical that is a combination of S1 and S2. Similarly, any combination of concentrations on this line would be a combination of S2 and S3. Similarly, any combination of these three substances, S1, S2, and S3, would lie within this plane defined by these 3 points. And we can see that Q1 lies inside this plane, which means that it lies within the convex hull formed by S1, S2, and S3. Similarly, we can see that Q2 lies outside this particular set. So that means that Q2 cannot be formed by a combination of these 3 chemicals. So problems like these are a natural indicator of that we should use the idea of a convex hull. And we can observe that if a substance Q belonging to R square can be created using substances in S that is a subset of R square, if and only if Q belongs to the convex hull of the set S. So now let's formally define the problem. So the problem is defined as, given a set S of n points in Rd, construct its convex hull Ch of S. Another version of the convex hull problem is that given a set S of n points in Rd, identify those that are vertices of the convex set of S, which is essentially just a decision problem, and one is a constructive problem. And these problems are asymptotically similar, since one problem can be transformed to the other problem. So since we are doing active computation, we want a finite set of points, and we operate only on finite sets of points. And the convex hull for a finite set of points in the plane produces a convex polygon. So if we have a bunch of points, we can basically define the convex hull by just using those extreme points that form a polygon. In 3 dimensions, however, the convex hull is not a convex polygon, but instead it becomes a convex polyhedron. And then in even higher dimensions, that generalizes to a polytope. So now let's look at the lower bound on the computational complexity of the convex hull problem. So we know that the convex hull problem will output a polygon, or simply a cyclic enumeration of the boundary vertices. So we can also say that we are sort of producing a sorting of the vertices, and we know that the sorting problem has a lower bound of n log n. Now to find the lower bound for the convex hull problem, we will reduce the sorting problem to the convex hull problem in a polynomial time, which is going to imply the theorem that any algorithm for the convex hull problem requires an n log n time in the worst case. So how does this reduction happen? So assume we have a set X of n points that we wish to sort. So we're basically going to be lifting the points from the x-axis to a parabola y equals x squared by doing the mapping xi to the point pi, where pi is defined as xi and xi squared. So as you can see in the figure, we have a bunch of points, and we basically just map them to their respective positions on the parabola. So resulting points on the parabola would be, we will call that set P. And all of these points will basically lie on the convex hull. And the sorted order of the points along the lower hull would be the same as the sorted order X. And therefore we can reduce the problem of sorting to and compute the sorting through the convex hull. So some of the algorithms in for computing the convex hull problem are output sensitive. That means that they depend both on the n number of input points that we have and the h number of output points that we have. These algorithms are called output sensitive algorithms. And these have a potential of becoming more asymptotically efficient than theta of n log n algorithms when h is in the small o of n. And the lower bound for these algorithms is then n log h in the planar case. Kirkpatrick and Seidel basically devised an algorithm that achieved this in 1986, and then Chan improved upon this algorithm and provided a simpler algorithm in 1996 that could do the same. So before we look at the algorithms, we will go over an important assumption. We're going to assume that all the input points are going to be in general position. That means that there will be no degenerate configurations in the input. So therefore, for example, there won't be any 3 points that are collinear. So point sets in general position will remain in general position if they are perturbed infinitesimally. This is, however, in reality, this is not the case, and there are problems with precision and all when we design algorithms. However, we do this because it is a convenience and we can avoid dealing with a lot of special cases during algorithm design, since degenerate configurations do not have that much of an impact on the performance of algorithms. So there are a lot of algorithms that employ a lot of different techniques to compute the convex hull of a point set. We have listed a few of these algorithms: these Jarvis, March, Graham scan, quick hull, Andrews algorithm, the Kirkpatrick-Seidel algorithm, and Chan's algorithm. We will be looking at the first 3 algorithms only. So the first algorithm we're going to look at is called Jarvis-March. Jarvis-March is also known as the gift wrapping algorithm, and it was published in 1973. The algorithm begins with the counter I set to 0 and a point associated with that value of the counter, P0, that is known to be on the convex hull. Then we select the point Pi plus 1 such that all the points are to the right of the line segment Pi and Pi plus 1. This checking of the point Pi plus 1 to make sure all the points are on the right side can be done in O of n time by comparing the polar angles that are formed between Pi and Pi plus 1 and the x-axis. And then once we do that, once we find the point Pi plus 1, we increase the counter, and then we repeat until we circle through all the vertices of the convex hull, and then we return back to the original point. That would yield the convex hull in h steps. So as far as the performance and time complexity goes, Jarvis-March is among one of the least efficient algorithms for convex hull. It would loop h times within each of those h times it would loop n times. Therefore, the time complexity would be big O of nh. And it is also you can also notice that the algorithm is output sensitive. So the next algorithm we're going to look at is called the Graham scan. It is based on the incremental construction technique, where we start out with a basic structure and then we build upon it during every iteration. So the first thing we do is we select the lowest point in the point set P, and we call that point P0. And then we sort all the points in a cyclic fashion such that based on the polar angle formed between that point and the point P0. And then for each point we determine if going to that point would mean that we have to take a left turn or a right turn. If we have to take a right turn, then we determine that the second to last point is not part of the convex hull, but instead it lies inside the hull. And then we do the same thing for all of the previously visited points until we're only left with a left turn set. That means all the points were those where we had to take a left turn. And then we repeat this process until we reach the starting point again in a counterclockwise fashion. This is a pseudocode for the algorithm where we've implemented this with a stack. So as far as the time complexity of this algorithm goes, it is a much more efficient algorithm compared to Jarvis-March. The sorting procedure is done in O of n log n time, depending on the sorting algorithm used. The loop seems that it runs in O of n square times, but the special thing about the Graham scan is that we delete all the points that we've already visited once. So because we're only visiting each point at most twice, the complexity of the loop is big O of 2n, which simplifies to big O of n. And then, so basically the time to sort the points is what dominates the time complexity of the algorithm. Therefore, gram scan is in big O of n log n. So the last algorithm we're going to look at is the quick hull algorithm, which is a divide and conquer algorithm, and is also based on the strategy of triangular expansion. It is also used for computing the convex hull in even higher dimensions because of its efficiency. It also uses the prune and search approach, where it reduces the input space by a constant factor at each step. So let's go over the pseudocode for the algorithm. So the first thing we do is we find the point with the minimum and the maximum, find the 2 points with the minimum and the maximum x coordinates. And then we use the line that is formed by these 2 points to divide the set into 2 subset of points. So let's call this line the baseline. So we basically divided the problem into 2 subproblems. So let's look at one of these subproblems. We determine a point on one side of the line which has the maximum distance from that baseline, and then that point and the baseline would then form a triangle. So all the points that would lie inside the triangle cannot obviously be part of the convex hull and are therefore completely ignored in the next steps. And then we keep repeating these previous 2 steps on the lines that are formed by this triangle. So that is where the recursion step comes in. And then we keep doing this until there are no points left. So either they're ignored or they're part of the convex hull. And the points that have been selected are then constitute the convex hull. So we divide the set of points into 2 subsets, and then we create a triangle, and then we basically repeat that for each line. And like this would extend till here, and then this would extend till here, and then all of that will merge into the convex hull, which is why this algorithm is a triangular expansion, uses the triangular expansion strategy. So as far as the performance goes, finding the extreme points is an O(n) operation. Quick hull divides into 2 subproblems, and in the best case, when the points are uniformly distributed over both sides of the line, then we can have a very simple recurrence where our process is O of n, and we divide the subproblem into 2 subproblems, and the subproblem size is half. So then we have a recurrence relation, and then we can solve the recurrence relation to find that the worst case complexity is big O of n log n. However, in the absolute worst case, when all points lie on one side, this can degenerate to n Tn minus 1 plus Cn, which means that the worst case would be quadratic. Also, this is called quick hull because of its relation to, or it's a sort of based attribute to quicksort, because it also partitions the input space into different subsets, like the way quicksort partitions the input array into subarrays. So the convex hull problem also has a lot of applications in 3 or more dimensions. So if you remember, we saw an example about mixing certain chemicals. In that example, we had 2 chemicals A and B. If we had 3 chemicals, we would be plotting the points in 3 space, and our convex hull problem would become a 3-dimensional convex hull problem. So if we are in 3 dimensions, the convex hull that we find is a polyhedron, or a 3-polytope. In higher dimensions, we have an n-dimensional polytope. And in this case, we're concerned with the facets of a polytope, or the faces of a polyhedron. And the convex polytope is basically the convex hull of all the vertices inside. This is obviously a significantly more complicated problem, which is both harder to visualize and also harder to implement. So the most famous and the simplest algorithm for the 3D convex hull problem is the gift wrapping algorithm. It is basically an extension of the 2-dimensional Jarvis-March algorithm that we saw earlier. The steps of the algorithm are: first, you find a facet that is guaranteed to be on the convex hull. Then you repeat this process. First, you take an edge E of a face F that's already on the convex hull, such that the face on the other side of the edge has not been found yet. So, and then for all remaining points pi in the entirety of the point set, you find the angle of the face E comma pi with the face F, and then you find the point pi which makes the minimum angle with the face with these 2 faces, and then you add the face with the minimum angle to the convex hull. So you can sort of see that we are basically you can sort of visualize it like using a gift wrapping paper. and then you put it on top, and then you're sort of folding it from underneath and trying to cover the entirety of the gift. This algorithm runs in big O of nf time, where f is the number of faces that we find on the convex hull. This algorithm also extends to n dimensions, and the n-dimensional convex hull is called an n polytope. The gift wrapping algorithm also extends to n dimensions, and there are also other methods such as the n-dimensional quick hull, Chan's algorithm, divide and conquer, and the beneath and beyond method. So we've looked at an overview of the convex hull problem, and we've only scraped the surface. There's still a lot more that we haven't been able to discuss, since the convex hull problem is incredibly deep and it has so many different ideas in both in a mathematical sense and also in the computational sense associated with it. Some of the references included Shamos and Preparata's book called Computational Geometry, an introduction, Michael de Berg's Computational Geometry, Algorithms and Applications, and the famous Introductions to Algorithm by C.L. Artis.